In astronomy, we study the nature of gravity, the universal force of attraction between masses. On Earth, we sometimes notice that objects can attract one another in two other ways. One is the familiar magnetic attraction of iron and certain other metals to a magnet. The second way is the attraction of an electrically charged object to other objects. We are all familiar with the way that a polyester shirt clings to the skin after a heavy coat is removed on a dry winter day. Also, if you comb your hair and then hold the comb near some light pieces of paper or wood shavings, the paper or shavings are attracted to the comb. In addition to attraction, repulsion can also occur to electrically charged objects. For example, if two glass rods are charged by rubbing them with some silk cloth, they will repel each other, as shown in the illustration. From these observations, we can say that the treatment received by the two glass rods was the same, and they must have the same charge. Therefore, objects having electrostatic charges of the same type repel one another, and conversely, those having different electrostatic charges attract one another. All of the elements of matter are composed of atoms. These atoms are the smallest particles which display the characteristic properties of a particular chemical element. The atoms themselves are composed of an extremely tiny central nucleus, which is surrounded by one or more electrons in orbit around it. This nucleus consists of positively charged particles called protons, and also neutral, uncharged particles called neutrons. The nucleus of a normal, non-radioactive atom is stable, and protons and neutrons are tightly bound together by what is called the strong force. The net charge of the nucleus itself is positive and depends upon the number of protons within it. The electron cloud surrounding the nucleus is composed of a number of negatively charged particles called electrons, after the Greek word electron, meaning amber. The negative charge of an electron is equal but opposite in value to the charge on the proton, but the mass of an electron is only about 1/2000th the mass of the proton. The neutron is similar in mass to the proton. In normal uncharged atoms, the number of electrons in the orbitals surrounding the nucleus is equal to the number of protons within the nucleus, and the total charge of the atom is zero, or neutral. The outer electrons in the metals can move from one atom to another and are called free electrons. These movable electrons are what constitute an electric current. Thales of Miletus, about 600 before the Common Era, was among the earliest to record his observations of rubbing amber with fur and causing a static charge. But most of our present-day knowledge of Thales is second-hand from later writers. We know that he studied geometry and astronomy, and he was able to correctly predict a solar eclipse. But he held the unusual belief that the fundamental element of the universe is water, and he attributed the electrostatic behavior he observed to a kind of life force. William Gilbert, who lived between 1544 and 1603, believed that electricity was a fluid existing in matter and able to flow through matter, and separate from the matter itself. Today, we still refer to electricity using the slang expression juice. Gilbert wrote a book titled De Magnet, which dealt with both static electricity and magnets, although no direct association between electricity and magnetism was evident at that time. His writings were a good mixture of observations and scientific method, as well as some incorrect speculations. The book did have an important influence on Galileo. In the year 1745, the Dutch physicist Pieter van Musschenbroek discovered that a jar partly filled with water and with a nail projecting from its cork could be used to store an electric charge. This was called a Leyden jar, in reference to the city in Holland where it was invented. The Leyden jar is similar in function to a modern capacitor. Benjamin Franklin, who lived from 1706 to 1790, performed his famous and extremely dangerous experiment with a kite, a key, and a Leyden jar during a thunderstorm. Lightning struck the kite, ran down the wet string, and charged the Leyden jar, proving that lightning was indeed a form of electricity on a grand scale. He He notes that the twine in the string repelled itself and stood out from the string. He writes, "And when the rain has wetted the kite and twine so that it can conduct the electric fire freely, you will find it stream out plentifully from the key on the approach of your knuckle. At this key the file may be charged, and from electric fire thus obtained, spirits may be kindled, and all the other electric experiments be performed, which are usually done by the help of a rubbed glass globe or tube, and thereby the sameness of the electric matter with that of lightning is completely demonstrated." Static electricity, once the charged object has been grounded, ceases to exist within the object. The objects return to a neutral state and no further flow of electrons takes place. Modern electric and electronic products and appliances, such as lights, radios, motors, and computers, require a continuous flow of electricity to operate. The first connections between static and current electricity were discovered by Luigi Galvani, who lived from 1737 to 1798. A lecturer of anatomy at the University of Bologna in Italy, Galvani had done experiments with frogs' legs and static electricity. He discovered that touching the nerves of severed frogs' legs with electrostatically charged metals caused the muscles to contract. However, during his experiments, he found that touching the nerves with dissimilar metals also caused the muscles to twitch, even when there was no static charge. He attributed this phenomenon to animal electricity, which he believed to be a vital force within all living tissue. Galvani was partly correct. Electricity does play a part in the functioning of living tissue, but in the case of the severed frog's legs, the source of electrical current was due to the dissimilar metals in conjunction with the moist tissue. Alessandro Volta was a professor of physics at Milan University who lived from 1745 to 1827. He disagreed with Galvani's interpretation of animal electricity. He did experiments of his own and constructed what was to be the first battery, called the voltaic pile. This consisted of a stack of discs of zinc and copper, or silver, alternately spaced with paper soaked in brine, that is to say, salty water. When wire was attached to the top and bottom discs, an electrical current was continuously available. The invention of the battery was quickly followed by a century of discovery and innovation. Electricity had transformed from a curiosity to a practical tool. The next slide asks several questions to help you check what you have learned.